Hello, everyone. In this video, we introduce the notions of basis of a subspace and dimension of a subspace. To introduce these notions, let's start with an example that we saw in the last section and in the last video. We had a matrix A given by these four columns, and we computed its reduced row echelon form to be this matrix here with 3 pivot columns and 1 non-pivot columns. What we saw last time was that the last column gave us information about the null space of the matrix. The null space is defined as the set of solutions to the homogeneous linear system, which in this case was the span of a vector given by essentially the coefficients of the last matrix. You have to solve the homogeneous linear system to check that this vector is a solution. And then we define the column space, which is nothing but the span of the 4 columns of the matrix A. Now, by looking at the reduced row echelon form and using the column correspondence property, we can infer immediately that the columns A1, A2, and A3 are linearly independent because the corresponding columns in the reduced matrix are, because they're different standard vectors. Recall, moreover, that the column correspondence property tells us how to write the non-pivot column in terms of the first 3. And that's just done using the coefficients of the column in the reduced row echelon form. So A4 will be given by 4/3 A1 plus 2/3 A2 minus 1/3 A3. Now notice that if I were to move A4 to the other side in this equation, so I would write something like this: minus A4 plus the rest is equal to 0. If I rewrite everything like this, or as I wrote it down here with a different sign, moving everything on the A4 side, you would get that the column correspondence property, the relation between the columns, gives us a solution to the homogeneous linear system. Because this expression here is a linear combination of A1, A2, A3, A4 that gives 0. In other words, is A times a vector X, the vector spanning the null space. And this little bit of algebra that we did here highlights the relation between the null space and the dependency relation in the columns of A. It's something that we've already seen, but it will show up over and over again. The next question is no longer about the null space, but rather about the column space. We know that the column space is the span of A1, A2, A3, and A4. In other words, A1, A2, A3, and A4 generate the column space of A. Can we find a smaller generating set? And the answer is yes, and once again provided by the same relation that we had here. Let me rewrite it as we initially had it written. A4 is equal to 4/3 A1 plus 2/3 A2 minus 1/3 A3. This tells us that we can generate A4 using just A1, A2, and A3. In other words, A1, A2, and A3 is a generating set of the column space of A, which is smaller than the initial one we had with A4. The next natural question would be, can I get rid of one more? And the answer is no, because A1, A2, and A3 are linearly independent. We'll see in a second why this linear independence of them implies that there cannot be a smaller generating set. The relevant definition at this point is that of a basis. If you have a subspace V of Rn, a basis of the subspace is a linearly independent generating set of the subspace V. So a basis is a generating set that is furthermore linearly independent. That's how you would think about it. Let's have a look at some examples. We saw the example above, in which we found that A1, A2, and A3 were a basis for the column space of A, and they are linearly independent by the column correspondence property. Other examples are whenever I get a set of standard vectors, the set of all standard vectors, they are linearly independent and they generate R2 in this case when there's only two. So they are a basis for it. And really, whenever you are in R2, picking any two non-parallel vectors will give you a couple of linearly independent vectors, and their span is the whole R2. So any two non-parallel vector in R2 are a basis. As I anticipated, the set of all the standard vectors is always a basis for Rn because they are linearly independent and they generate Rn. The last example relates this to the matrix theory that we had. Suppose I have a set of n vectors in Rn, then if the matrix whose columns are those vectors, v1 through vn, is equivalent to the identity, meaning that its reduced row echelon form is the identity, and this is the same as saying that A is invertible. Then, and only in that case, the set S is a basis for Rn. Okay. Let's have a look at some properties of what a basis does. And then in the next video, we'll talk about applications and examples. The first property of a basis is that whenever you have a generating set, you can always trim it down, taking out linearly dependent vectors until you reduce yourself to a basis. In other words, that's what's written in number 1. If you have a generating set, this will always contain a basis for your subspace. This is exactly the case we saw in example 1. Example 1 had a column space with 4 columns, a generating set of 4 vectors, and we saw that one of them could be avoided and trimmed out. In fact, the generating set contained the basis made up of the first 3 vectors. The converse to this is that if I get something that is potentially a basis, meaning that it's linearly independent, but it's not yet a generating set, I can extend it to a generating set and to a basis by adding vectors that are linearly independent. So yeah, if we look at these 1 and 2 together, what's happening is the following. A basis is a generating set that is linearly independent. If you have something that is only a generating set, you can remove vector until it's also linearly independent and get a basis. If you have something that is only linearly independent, then you can add vectors, keeping it linearly independent until you get also a generating set, therefore a basis. Those two properties combined have another consequence, which is the third property here, which is that given any subspace of Rn, every possible basis I pick for that subset has the same number of vectors in it. So the number of vectors that are in a basis does not depend on the basis that I choose. This allows us to define the dimension of a vector space, of a subspace. This dimension is exactly the number of vectors that there are in a basis. It doesn't matter which basis I choose, there will always be the same number of vectors. And so I call that number the dimension of my space. In the next video, we'll see some examples and some applications of this concept.